All right. So, writing and balancing chemical equations. So a chemical equation is exactly what it says. Okay, a chemical equation is an equality between reactants or reagents, you can call them reactants or reagents, and products. Okay. Now, the reactants are written on the left-hand side of the equation. So, left-hand side. The products are written on the right-hand side. So, reactants react to produce products. That's how you can remember. Now, you've probably seen these reactions. You've seen chemical equations written in, like, biology when we're talking about photosynthesis or glycolysis. So, they're not something that you haven't seen before, but we're just kind of looking at them in depth. Now, the total number of atoms on one side of the equation will always equal the total number of atoms on the other side. Okay, so the amount of stuff I started off with has to be the amount of stuff I ended up with. Okay, atoms don't just disappear and appear. Okay, it's not magic. So this is called the law of the conservation of mass. Okay? Law of conservation of mass. So that's really what the law of conservation of mass says, is that matter can neither be created nor destroyed. You've probably heard that, right? So when we're doing a chemical reaction, you don't just lose 2 hydrogens to the ether. You don't just appear with 2 more hydrogens, okay? And so to follow the law of conservation of mass, there are 2 things that we use to follow that. We use subscripts. We know what a subscript is. Okay, Unit 5, we learned that subscripts, we use subscripts to write formulas, right? So a subscript is the small number to the lower right of an element found within a formula. Okay, subscript would be like if you have water, this 2, that's our subscript. Okay? This is what you worked with when we wrote compounds. It only multiplies to what is immediately in front of it. Does this 2 multiply to the oxygen? No. Now, there is subscripts that multiply. Say I have, let's say it again. Say I have like calcium phosphate. Okay. This 2, this subscript will multiply to everything in the parentheses, right? But does it multiply to the calcium? No. Okay. Now, if an element has no subscript, it's an understood 1. So oxygen has no subscript, so there's 1 oxygen. If there wasn't 1 oxygen there, then the oxygen wouldn't be there. Okay? Now, a coefficient is a large number placed in front of a substance and used to balance a reaction. So, when we are writing a chemical equation, we want to make sure we have the correct number of hydrogens on both sides. Now, we can't change the formula of calcium phosphate, because where did these subscripts come from when we wrote this formula? Where did the 3 and the 2 come from? Balancing charges, right? Okay, so we can't change those subscripts. But say on my product side I had 6 calciums. What I can do is put a number in front, and that can balance the number of calciums. Okay, and I'm going to show you how to do that in a second. So this coefficient multiplies every atom in the formula by that number. Okay? So if I put a 2 in front of calcium phosphate, that 2 is going to multiply to the calcium. That's going to cause 6 calciums. That 2 is also going to multiply to the phosphate. 2 times 2 would be 4 phosphates. Do y'all see that? So big numbers affect everything behind it. Little numbers only affect what's directly before it. Okay? Now, it indicates the number of formula units of the compound. No coefficient would be understood. If there's no coefficient, it's an understood 1. So if you don't have a coefficient in front, there's just 1. Think of this like a recipe. Okay? If you need 2 cups of flour, you put 2 cups. You would measure out 2 cups of flour, right? Same here. This recipe for this formula means I need 2 calcium phosphates. Y'all see that? And then if I broke it up again in calcium and phosphorus, it'd be I need 6 calciums and 4 phosphates. Okay? Now, steps to writing a balanced equation. Okay, there are a lot of steps. And again, we're going to do some practice with this. So usually what's going to be given is a word, it's what we call a word equation. Okay, it's literally a sentence that describes this and this reacts with this to form this and this. Okay, you're going to have to write your formulas, reactants and products. You're going to have to write coefficients in order to balance all the elements in that compound, or in that reaction. Okay, so number 1 says write a correct formula for each of the reactants reagents. Okay, so our first step is we have to write a correct formula. Now, what you'll notice is that if you do not write a correct formula, your balancing will be off. If your formula is incorrect, your balancing is incorrect. Okay? Sometimes you can balance it, but I mean, it's wrong. Your recipe's wrong, which means the reaction wouldn't happen. Okay? Or it would happen funky, or like you have some left over. There's a lot of things that can happen, but essentially that's what happens. Now it says write the correct formula for each of the reactants. So if we have water and sodium, okay, you write the formulas for that. It says put a plus sign between the reactants to separate them. Plus signs do not mean combine. Arrow means combine. Okay? Plus signs means this and this. That's what it means. Flour and sugar combine to form cake. Y'all see that? Okay. So, a plus sign indicates added to or reacts with. Okay? These are my two reactants. These are my two compounds that are going to react. Okay? Now, note, if an element is by itself, this is only if it's by itself. Sodium's by itself. Chlorine's by itself. Sulfur's by itself. We have to check and see if it is diatomic. You remember the diatomic elements? Okay? Diatomic, I bring clay for our new house. Okay? Iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen. Are you having a periodic table? Yes. So on your periodic table, it's easy to remember. Hydrogen, diatomic. Okay? Then go over and make, say, 7. Nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. If any of these elements are by themselves, they are considered diatomic. If they are in a compound, they're not diatomic. Okay? That's when you use like either charges if it's a covalent, or ionic charges, balance them. Or if it's covalent, use prefixes. Okay? So those are only if they're like by themselves. If it's hydrogen and oxygen, that'd be H2 and O2. Okay. Now, the next step is draw a yield arrow. So we wrote our formulas for our reactants, this and this. We're going to draw our yield arrow that you may see in the question. You may see words like to produce. Okay, to produce. Or you may see yields. Okay, reacts to form. Okay, reacts. Those are key words. Those all mean draw an arrow. Okay, that's where the magic happens. In that arrow. Okay? So we draw our arrow. Next step, write the correct formula for each of the products. Putting a plus sign between them also. So then we do our products. They react to form water and sodium chloride. Okay? Next, balance out the entire reaction by changing the coefficients. Okay? Next step is you're going to look at your reaction. You may have 2 hydrogens on one side and 1 on the other. That does not mean that hydrogen just disappeared magically. Okay? That means we have to use coefficients, those big numbers in front, to balance those. Now it says do not change the subscripts. Can we ever change a subscript? No. You change a subscript, you change the compound. We can only put the numbers in front. Okay? This is what it means by balancing. Because you may have to go back and forth like you balance. Okay? Your goal in this step is to try to get the same number of each kind of atom on both the reactant and product side. I want 2 hydrogens in my reactant, I want 2 in my product. So I'm going to put a 2 in my product in front of that compound to make 2 hydrogens. Now, the tricky part about this is that 2 in front may change the hydrogens, but it may change a chlorine too. Okay? So then you have to go back and balance chlorines. And go back and forth. That's why it's called balancing. Back and forth. Now, your goal in this step is to try to get the same number of each kind of atom on both the reactant and product side, satisfying the law of conservation of mass. Okay? It's best to balance in the following order. So, I'm going to show you kind of what I do to balance. I'll list underneath the arrow. In the following order, you want to balance metals first, then polyatomic ions if they stay together. So sometimes you'll have a phosphate in your reactants, phosphate in your product. Keep that phosphate together. It's a lot easier to balance a PO4 than phosphorus and oxygen separately. Okay? If they separate out, if you don't see, say you have a chlorate in your reactant, but then chlorine and oxygen are 2 different compounds, you're going to have to separate them out when balancing. You can't keep the chlorate together. Okay? Non-metals and then hydrogens and oxygens are always last, because those are usually the trickier ones to balance. Okay? Coefficients cannot be placed in the middle of a compound. You cannot do Ca3,2,PO4,2. Okay? You cannot put a coefficient in the middle. It always goes in front. It always affects everything in that compound. Okay? Finally, place the phase in parentheses next to the substance to indicate the physical state. S is for solids. This means crystals and precipitates. Did we talk about a precipitate? I can't remember if we've talked about precipitates before. We'll talk about that in a second when we look at the solubility rules. Precipitate is a solid that forms when 2 solutions are mixed. Okay? So, you mix 2 solutions. There's a solid that forms in the solution. It's called a precipitate. G is for a gas. So it may say hydrogen gas. Water vapor would be a gas. L, now that's like a cursive L. Okay? That's why it looks kind of weird like that. Usually I'd do it like this. L. Cursive L. Stands for pure liquids. Now this is pure liquids. This is liquid water or a melted compound. Okay? And then AQ stands for aqueous. Okay? Aqueous means dissolved in water. So if you have sodium chloride dissolved in water, you put that AQ next to it, right? So you remember with acids, we always put AQ next to acids. Okay? Now, states for single elements can be predicted by looking at the periodic table in our classroom on the wall. So if it's black, that means it's a solid. Okay? If it's blue, it's a liquid. If it's red, it's a gas. So if you just said that, if it just says that hydrogen and oxygen react, you put a G next to hydrogen, G next to oxygen, because that's what our periodic table tells us. Sodium's a solid, so you put Na with a solid. Mercury's a liquid. Mercury's the only liquid metal. Bromine's the only liquid nonmetal. Okay? Sometimes you'll use that periodic table to figure out states. Some periodic tables can be funky. They'll put gallium as a liquid, but gallium's not a liquid unless it's like at body temp, not room temp. This is the states at room temp. Okay? Does that make sense? Okay. Now, it says metals are all solids except liquid mercury. Nonmetals, hydrogen, nitrogen, oxygen, fluorine, chlorine, and group 18 are gases. Bromine's a liquid. The rest are solids, like silicon, phosphorus, sulfur, selenium, arsenic, all of them. Okay. States for ionic compounds when water is not present. So if water is not present, your ionic compound is going to be a solid. If water is present, it's going to be either aqueous, or if it's a precipitate, you're going to put it as a solid. Okay? Now, states for ionic compounds when water is present can be predicted using solubility rules. You're going to be using these a lot. Okay? Now, on the test, you will be given, well, no. I can't remember if you're given solubility rules or not. I don't think you're given solubility rules, but you are given the activity series. I'll have to look at that. We know water is present. Oh, yes, so, duh. It says you will get these rules on testing quizzes. So, we know if water is present either by having water in the reaction, or if it says a solution, it says this is a solution, or if there's an acid. Acids are only acids if they're dissolved in water, right? So, these are the solubility rules. This is how to read if an ionic compound is going to be solid or liquid. Or, sorry, aqueous. So, soluble compounds. This means that they will have a designation of aqueous if compounds have these ions. If all group 1 salts, meaning group 1 metals, lithium, sodium, potassium, rubidium, cesium, francium, if any of these are in my formula, it's automatically aqueous. And notice there are no exceptions, right? If I see sodium, aqueous. Potassium, aqueous. Period. Okay? All ammonia salts, ammonium chloride, ammonium phosphate, whatever has ammonium, always going to be aqueous. There are no exceptions. Okay? All nitrate, chlorates, perchlorate, and acetate, no exceptions. If there's a nitrate, cobalt nitrate or cobalt-2 nitrate, or silver nitrate, or strontium nitrate, those are always going to be aqueous, period. So if you see any of these, put an AQ, move on. Okay? Now, all chlorine, bromine, and iodine salts are aqueous unless, okay, if you have a chlorine, bromine, or iodine, they're all aqueous unless bonded with silver, mercury, or lead. Okay? If bonded with silver, mercury, or lead, that makes it a solid. That makes it a precipitate. Silver chloride is a solid. Sodium chloride is the aqueous. Do y'all see the difference? So if I see I have a chlorine, but it's bonded to silver, solid. If I have a bromine bonded to lead, solid. Okay? That means it's not dissolving in water. It can't dissolve in water. Next one. All fluorine salts, unless bonded with mercury, calcium, strontium, barium, lead. Okay? Not mercury, sorry. Magnesium. Wow. Magnesium, calcium, strontium, barium, and lead. Those are going to be solids. So, strontium fluoride, solid. Lead fluoride, solid. Calcium fluoride, solid. All salts of sulfate are going to be aqueous unless bonded with these. Okay? All of these are aqueous unless bonded with, or all sulfates are aqueous unless bonded with calcium, strontium, barium, silver, mercury, lead. Okay, so you have to check the solubility chart when writing ionic compounds for a reaction. Now, all of these are insoluble, meaning they're solids, with exceptions. Okay? So all hydroxides are going to be solids unless bonded with group 1, ammonium, calcium, strontium, barium. So sodium hydroxide is going to be aqueous. Sodium hydroxide is aqueous. Magnesium hydroxide is going to be a solid. Okay? Calcium hydroxide is aqueous. Barium hydroxide is aqueous. Okay? But if I have iron 2 hydroxide, solid. And then all other monoatomic and polyatomic ions. If you have like a perchlorate, not perchlorate, sorry, that's the wrong. Say you have a dichromate. All dichromates are solids, unless bonded with group 1 and ammonium. Okay, because group 1 and ammonium, remember, they don't have any exceptions. Okay. So, let's look at how we can write these equations. So, it says write a balanced equation for each of the following reactions. You will need to predict some of the states based on the rules on the previous page. So, some of them, it may not say solid. But if it's not in water or if it's an element by itself, use your periodic table, right? Okay? So, and we'll have to use the solubility rules above. First step, and look at it. A piece of zinc reacts with hydrochloric acid to produce zinc chloride and hydrogen gas as the products. Okay? So first thing I see is I have a piece of zinc. Now this is just an element, correct? Is this element diatomic? No. Zinc is an element by itself. Look on the periodic table. Is the zinc a solid, liquid, or gas? Solid. Okay, so when I put a piece, solid zinc. Now I see the word, or words, reacts with. What does that mean? That means I'm going to put a plus. Okay? Now, hydrochloric acid. This is where our nomenclature comes in, right? Hydro in front means that the anion is just chlorine. What is the cation for acids? All acids have a cation of hydrogen positive 1, right? So we have hydrogen positive 1, chlorine negative 1. What's our formula? HCl. Now, all acids have a designation of what? AQ. I see that zinc and hydrochloric acid, if I drop that piece of zinc and hydrochloric acid, the reaction's happening in water, correct? So I can assume my products are going to be produced in water. Okay? Now, to produce means I'm going to put an arrow. Okay? Zinc chloride. Zinc chloride. Now, zinc, it's a transition metal, but there's no Roman numeral. Why? Why is there no Roman numeral? Because it's always going to have a set charge, which is positive 2. Yeah. Close. Positive 2. Chloride is just chlorine with a negative 1. So our formula is ZnCl2. Okay? Now, what's our state going to be for zinc chloride? Well, this is reactions happening in water, right? We need to look at our solubility rules. Is there any rules for zinc? Do you see any rules for zinc over here? No. Do you see any in the exceptions? No. Do you see any rules for chlorine? Yes. Where do you see the rule for chlorine? Right here. All chlorides are aqueous unless bonded with silver, mercury, or lead. Is zinc chloride one of those exceptions? No. So, zinc chloride is going to be aqueous. Y'all see the conclusion I went there? Y'all sit up, please. Guys, y'all sit up. You wake them up. Thanks. Wakey, wakey. Okay. So, it's aqueous. Then I see the term and. That's going to mean plus. Hydrogen gas. Hydrogen by itself. It even tells us it's a gas. But there's also kind of a alarm bell that should be going off. What is it? What's the alarm bell that should be going off here? Diatomic. Hydrogen is diatomic. It's only diatomic when it's by itself. Is hydrogen diatomic here? No. It's only diatomic when it's by itself. Okay, hydrogen gas means it's just hydrogen. Very flammable. Okay? Alright, so let's set up our reaction. We have zinc, that's a solid, plus hydrochloric acid, which is aqueous, yields zinc chloride, ZnCl2, which is aqueous, plus hydrogen gas. Okay? Now, we've written our equation, but is it balanced? Are we following the law of conservation of mass here? No. What do you notice? Look at the numbers of hydrogen. Is it the same number of hydrogen on both sides? No. Is it the same number of chlorine? No. Okay? I got to use coefficients. This is how I balance. Okay? Sometimes people can just look at it and balance it easy. This is how I balance. So remember, metals first. Zinc is a metal. Okay? Then polyatomic ions. Are there any polyatomic ions? No. Non-metals, I see I have a chlorine. And then hydrogens and oxygens are last. Okay? What I do is I'll list all the elements and polyatomic ions that are in our reaction underneath that arrow. Okay? Now, how many zincs do I have on my reactant side? 1. I have 1 zinc on my reactant. How many do I have in my product? 1. Okay? Chlorines. How many chlorines in my reactant? 1. How many in my product? 2. There are 2 chlorines in my product. Hydrogen. How many in my reactant? 1. How many in my product? 2. Okay? So, my zincs are good. I got 1 on each side. We're balanced there. Here, I got 1 chlorine in my reactant, but I have 2 in my product. So, I'll look at my formula that has chlorine in it. What can I put in front of hydrochloric acid to make chlorine 2? 2. If I put a 2 here, That's changing my chlorine to 2, right? What else is it changing, though? My hydrogen to 2. But look what that did. After I put the hydrogen, or after it changed the hydrogen to 2, it automatically balanced it, right? So, do we need to add any more coefficients to anyone? No. The rest of them, there's an understood 1. Okay? It's not 0. If it was 0, it wouldn't even be in the equation. Why would we even put it there, right? So the rest of them have understood 1s. I like putting the 1s there because you're actually going to be using these coefficients to in conversions later on. So that just kind of helps me. Oh, there's 1 zinc. Okay? So this is like a recipe. This is what an equation does. 1 zinc and 2 hydrochloric acids will react to form 1 zinc chloride and 2 hydrogen molecules. Okay? Now let's look at the next one. It says phosphoric acid is reacted with a solution of sodium hydroxide to produce sodium phosphate and water as the only products. Okay, phosphoric acid is our first one. Is there a hydro in front? No. That means we're dealing with a polyatomic ion, right? Ick means we're dealing with a what kind of polyatomic ion? 8. Okay, remember 8 something icky. Okay, 8 something icky. So this is phosphate, which is PO4. What's our charge? -3. Okay. What's our cation for acids always? Hydrogen, +1. So what is my formula for phosphoric acid? H3PO4. Okay. Acids are state always aqueous. Okay. Now is reacted with, that tells me I got to put a plus sign. A solution. Solution tells me my state is aqueous. Okay? Of sodium hydroxide. And you can double check sodium hydroxide. +1, hydroxide, -1. Our formula is NaOH. You can double check your solubility and make sure it actually is aqueous. Sodium's a group 1 metal, right? It's always going to be aqueous. If I see a sodium in front, just tack that aqueous on. Okay? Now, to produce, arrow, sodium phosphate. We said sodium's charge is +1. Phosphate is PO4, -3. So what's our formula for sodium phosphate? Na3PO4. Now, again, double check your solubility. Sodium phosphate, well, it's got sodium, that's a group 1, so it's going to be what? Aqueous. Okay. And water. What would water's state be? Liquid. Okay? Pure water is always a liquid. Now, the reaction is happening in water already, but what this water represents is new water being formed. Okay? The reaction's happening in water, but I'm forming new water. Do y'all see that? Okay. This isn't just left over from the reaction. It's new water. So write our formula, or our equation, H3PO4 plus sodium hydroxide, which we said was aqueous, yields sodium phosphate, which is aqueous, and water, which is a liquid. Okay? So there's our equation. Now we need to balance. So look at it. Is it balanced? Do we have the same number of each element on both sides? No. Okay, we need to balance this. Now, I see I have sodium. Okay, so write your sodium. I have phosphate. This is polyatomic ion. I see hydroxide on this side. Do you guys see a hydroxide on my product side? No. Now, here's a little trick that will help you balance. Okay? I don't see a hydroxide on my product, but I see water. Water's ionic name, if it were written ionically, is actually hydrogen hydroxide. Okay? Water's ionic name is hydrogen hydroxide. If I write water as hydrogen hydroxide, when balancing, I can keep those hydroxides together. That will make my balancing easier. Do y'all see what I did there? Okay? So this hydrogen is separate from this. OH is together, hydrogen's together. Or hydrogen's by itself. Okay? And then I have this hydrogen is going to be separate. Okay? So that helps balancing a little bit. I'm not having to take into account hydrogen from here and hydrogen from here. Okay? So, I have 1 sodium in my reactant. How many do I have in my product? 3. How many phosphates in my reactant? 1. How many in my product? 1. How many hydroxides in my reactant? 1 OH. How many OHs in my product? 1 OH, right? This is 1 OH. How many hydrogens in my reactant? 3. How many hydrogens in my product? 1, right? This hydrogen is part of hydroxide. That doesn't count towards the number of hydrogens. Y'all see that? Okay? This hydrogen was already accounted for in the hydroxide, so I have 1 hydrogen here. Okay? So now, I'm going to start to balance. I see my sodiums aren't balanced. I'm going to put a 3 here. That changes my sodium to 3. What else does that change? It changes sodium to 3 and hydroxide to 3. Right? So phosphates are good. Hydroxides, I got 3 in my reactant now. So what can I do over here to balance my hydroxides? Put a 3 here, right? 3 times 1 hydroxide. That changes my hydroxides over here to 3. That changes the hydrogens to what? To 3. Did that balance it out? Yes. Okay. So again, double check. 3 hydrogens. 3 hydrogens. 1 phosphate, 1 phosphate. 3 sodiums, 3 sodiums. 3 hydroxides, 3 hydroxides. Okay. Now, it's understood 1 for the rest. Okay? Now, I'm going to skip the next 2 examples, move on to 5 types of reactions. Okay? This is just identifying the types. Later on, we're going to learn how to predict the types. Okay? So this is just identifying. 5 types of reactions: synthesis, decomposition, single replacement, double replacement, combustion. Okay? Now we're also going to talk about what we call redox reactions. Okay? A lot of these can be redox and decomp, or redox and synthesis. Okay? But these are the 5 types. Now, to identify the types, synthesis is an element plus an element coming together to form a compound. Or you can also have, for synthesis, you can also have a small compound plus a small compound combining to form one big compound. Big thing to identify with synthesis, there's no plus sign on our product side. Do you see a plus sign over here? No, that's synthesis. Okay? Next one, decomposition is the opposite. Because when you decompose, you break apart, right? Decomposition is a compound breaking down into an element and an element. Or it may be a compound breaking down into smaller compounds. You can see that also for decomposition. Big thing here for decomp, there's no plus sign on our reactant side. It's just a compound on the reactant. So synthesis, just a compound in the product. Decomposition, just a compound in the reactant. Okay? Next is single replacement. Single replacement is a compound plus an element combined to form a different compound plus a different element. Okay? So notice what happened here. We had AY plus X forms AX plus Y. So the Y and the X switched places. Y'all see that? You can also have AX plus B forms BX plus A. In this case, the A and the B switch places. Okay? So it's like cheating. Think of it that way. Cheaters go from one person to another. Okay? Next one, double replacement. It's like a swap. So we have double replacement is a compound plus a compound yields to form a compound plus a different compound. So AX plus BY forms AY plus BX. X and Y switched partners. Okay? X is now with B, Y is now with A. Now the last one, combustion, is usually an organic compound. So an organic compound has carbon, hydrogen, can have oxygen, nitrogen, whatever. It's an organic compound plus oxygen. So we're an organic compound plus oxygen. And it's always going to form carbon dioxide and water. Okay? Now there's several different other types of combustions that don't form just carbon dioxide and water, but the combustions we're looking at in this class form only carbon dioxide and water. Okay? You can have combustions with nitrogen and sulfur, but we're not going to deal with those. Okay? Alright, so looking at these, it says, for each of the following reactions, state which classification of reaction they represent. So, we have 2KNO3 yields 2KNO2 plus O2. What kind of reaction would this be? Decomposition. Do you see a plus sign before the arrow? No, so this is decomp. Okay. Next one, KBr plus Cl2 yields KCl plus Br2. What kind of reaction would that be? We have a compound plus an element yields a compound plus an element. What is that? Single replacement. Single replacement, the cheater. Okay? They switched. Chlorine and bromine switched. Chlorine stole bromine's girl. Or boy. Or whatever. Okay? Next one. We got a compound plus compound. Aluminum nitrate plus sodium hydroxide yields aluminum hydroxide plus sodium nitrate. What kind of reaction is this? Double replacement. They swapped. Next one, CH4 plus O2 yields carbon dioxide and water. What would that be? Combustion. Anything organic compound plus oxygen, if it forms carbon dioxide, water, combustion. Next one, we got iron plus sulfuric acid yields iron, what is that? Iron 3-sulfate plus hydrogen gas. What would that be? Single replacement. How do I know it's single replacement? Element, compound. Okay. Last one. CO plus O2 yields CO2. What would that be? Synthesis. This is tricky because it may look like it's combustion, right? We got an organic compound plus oxygen, but it only formed carbon dioxide. It didn't form carbon dioxide and water. Okay? So it's two. So remember, sometimes it's element plus element, or it can be a compound plus a compound form a bigger compound. Okay? So that's synthesis. All right. So what I want y'all to do now, you're going to be working on your practice worksheet. You'll be doing pages 1 and 2. Okay, pages 1 and 2 in your practice worksheet.